Now, you've probably done this before, but OSI, ISO, OSI. This is short for International Standards Organization, Open System Interconnection. I'll ask a few questions and see how we remember it. If we remember it, maybe we'll save the time. If not, we'll go through it. If you are very happy and you know and you've done it before, and you're welcome to head off if you like. We're going to spend the next 20 minutes talking about OSI, Open System Interconnection. Right, I'll ask a few questions, very simple questions. How many layers are in the OSI model? 7 layers. My original question, how many layers on the 7-layer model? So they call this the 7-layer model because there are 7 layers. Right. You need to know the names of those layers. Everybody knows those layers? We start with number 1. What's the name of the first one? Physical layer. The next one? Data link. Network layer. Number 4?
I know the first 3. Number 4 is transport.
Yeah, thank you. I wasn't asking you. I have another volunteer here. Number 4? Do you know the name of the number? Transport. No. And number 5? Session layer. Number 6? Presentation. Oh, very good. It's all right. Okay. So, right. Why did they come up with the model, with this model? What's the purpose of having this 7-layer model? Why did they come up with it back in the 1970s? Yeah.
Supposed to visually demonstrate the flow control of data, or how signals move.
They actually didn't say, guys, how are we going to demonstrate the flow of data? Let's create a model. That's not the reason why they said, let's create a model. They created a model for another reason. Yeah?
So that everyone was using the same model?
So hopefully all communication systems, if they follow the same system or the same model, that computers can communicate together. That's why they call this the open system interconnection. In the older days, when computers started communicating, IBM computers could only communicate with IBM, and other manufacturers could only communicate with the same manufacturer. Because everybody had their own way and their own vision and their own model and their own design. So the ISO, which is the International Standards Organization, they decided to come up with a standard. So the standard is such a model that if all manufacturers follow it, hopefully we'll have computers communicating to one another. And in fact, it was one of the most successful standards ever produced because all computers today communicate together. Like the television is about 60 years before computers came out, and they had standards for them and models, but up to today, if you get a computer or a television manufactured in America, it wouldn't work in Europe. And if you take a European television, it wouldn't work in Japan because they still have different standards. It wasn't as successful as the communication standards for computers. So this model was pretty handy and it did the job pretty well. And the International Standards Organization belongs to the United Nations. So it's a branch of the United Nations, and it's called the International Standards Organization. And it has members of a lot of countries, almost every country in the world, and also the big major companies that are involved into communication and computers. So they got together and they came up with this system that they thought it will solve the problem of communication, and it did. And just remember that the model does not tell you how to actually do something, it tells you what the outcome is, what you should produce and send to the other party, not how you actually do it. It doesn't tell you how do you detect the errors. Find some way of detecting it, but as long as you can do it with the other side. So they decided to have multiple layers, and every layer has its own job or is responsible for certain functionalities. So we have the 7 layers. And I'll go briefly through it. So they call the first one the physical layer. And the physical layer, they say, it's responsible for transmitting signals. That's all it is responsible for. It doesn't know anything else. It doesn't know frames, it doesn't know packets, it doesn't know users. It's only if we say, here's a list of bits, send them through either an electric or wire or wireless or radio signal or fiber optic or light signal, whatever it is. So all it does, it sends data to the nearest device, and it only talks to the nearest device. It doesn't go beyond it. So the next device can send data to the next device. So every device, ideally, should have a transmitter and should have a receiver. Something that transmits a signal, and the other guy receives, and this one transmits, receive, transmit, and so on. So this is the... Remember now, all these 7 layers are all in one machine, in your machine. The last machine, so the user is sitting at the top. It's like, imagine you're the user, you're looking at your computer downward like this. This is the screen of the computer. And that's the transmitter, the wire that comes out of your computer. Everything else is in between, inside your machine. So they have a few kind of guidelines in this model. One of the guidelines, they say, is that communication happens between opposite entities. Like a user communicates with a user. Imagine he's a company. A user cannot communicate with somebody else on the other system. So every entity can only communicate with its peer entity. They call them peer entities. That means entities at the same level. So a transmitter at the physical level, level 1 or layer 1, can only communicate with the machine at level 1 as well, with another receiver on the same level. They cannot look any higher. So that's one idea. Communication only happens at the same level. So let's say somebody at level 4 here can communicate with somebody at level 4. We call this, number 4 is called the transport layer. And this form of communication, they call it between all layers. Remember that there are 2 ways you can consider communication. You can consider that there's something called virtual communication. That's a communication that appears to be happening, but it doesn't really take place at this level. So all communication, you can look at it as into 2 forms. Either virtual, so a user holding a phone talking to another user in Australia, they can almost imagine their image, and they think they're talking directly to that person over the phone. In reality, that's not where the communication happens. In reality, the sound goes into the speaker or into the microphone, translated into English signal, it goes down to the nearest switch to the device, transmitted, goes from one switch to the next, and then maybe it goes over satellite back down into the phone of the other machine, and it's translated back into sound. So that's the real route or the real communication. So there are always 2 forms of communication. One is known as virtual. You think in your mind, that's who you're communicating, how you're communicating. In reality, there is another route. So there's a real communication that goes down through the layers, up through the layers on the next device, intermediate device. That's a router, goes up and down through the next router, and then up finally to the last machine and up to the user. This is the real communication. But remember also, there is virtual communication. Virtual communication is not real. It appears to be happening. Mentally, that's what you think is happening. In reality, that's the real path that the actual communication takes.
Is virtual communication only in the top 3 layers, or it can be any
No.
layer?
Okay, where does real communication happen and where does virtual communication happen? Virtual communication can happen at any layer except one layer that doesn't have virtuality. It only knows real communication. Which layer is that? Layer 6 or 7? Anybody knows? Layer 1. Layer 1 has no virtuality. Layer 1 is the only layer that physically data actually move from one machine to another machine. Otherwise, it's all on your machine and you're on the same device. This is like the post system. Once you post a letter here as a user, hand it to the postal system, and they move it around within the post system in the same city in Dublin. Only when they put it in an aeroplane to go to London, that's the real physical movement. Otherwise, it's still in the same place. And in London, they look at it and they say, oh, this letter is not for us, it's say for Turkey. So they put it back, send it back to the airport, put it into another airplane to Rome. And in Rome, same thing, until it eventually gets to Istanbul, where they say, oh, that's for us, bring it up, and they deal with it. So that's really what happens. These devices in the middle here, the model called them intermediate devices. Now we know them as routers. So this is a router, or a switch, or whatever the device that we want to call it, but in the model called it intermediate devices. Intermediate devices like routers don't have users sitting at them, don't have level 4, 5, 6, or 7. They only have the first 3 layers. So every device, doesn't matter whether it's a router or an end user device, must have transmitter and receiver, must have physical layer. Now, there is another rule concerning this model. They say we have one layer only to serve the layer above it. So all these layers, every and each layer here has a function. And the main general function is to provide service to the layer above it. So this model also works kind of on a master kind of slave idea. Let's say the user says, I want to communicate with somebody in Australia. All it has to do is ask the next layer. It says, call me this guy. So this one here is called the application layer. And what's the application layer? It's any program that allows you to communicate without really you need to know much about the communication or networking. Let's say email system. You run it, the user says, run the email and say, send this email to my friend in Australia. That's all it does. So the user requests the operation from the application layer. The application layer requests what it needs from the next layer below it, and so on. Every layer asks the layer below it. One of the examples here is, again, each layer is responsible for certain jobs. So these are some of the basic ideas. Every layer has certain jobs to do. And the layer above it can ask it for it, can't tell it how to do it. Just say, get me a virtual circuit, for example. So layer number 2 is called the data link. And its main job is to make sure that the physical layer works correctly. As far as the layer above it, which is called the network layer, so if this guy says, I want to send a message to the next machine, the data link layer makes sure that the transmitter transmits it to the next machine correctly. So it probably will do error detection. Some of the jobs that we'll do here is probably error checks or error detection. And also solve the flow control problem. Remember flow control? We looked at the data link layer. It has error detection issues, it has flow control issues, and maybe a couple of other problems. So that's specifically the jobs of the data link layer. But its overall job is to make sure that when something is transmitted by the physical layer, it's transmitted without any errors, and there are no issues there. But once it's transmitted, it's always given to the next layer to decide what to do with it. That's the network layer. So the network layer is responsible for routing. This is the only part of the system that knows the network, that knows routing. So it's responsible for routing. It's responsible for congestion control. Congestion, that's heavy traffic in the network, it can control it. It's called congestion. And it's also responsible for virtual circuits. Remember, we talked about virtual circuits, switching technique, how to create a virtual circuit and delete it. It's done at this level. Usually, level 4 will say, hey, I need a virtual circuit. It'll ask level 3. Level 3 goes and creates virtual circuit and comes back and say, here's your booking code, here's your virtual circuit number. So this guy is there to make sure routing is done correctly, congestion, the networks don't have any heavy traffic too much to deal with it, and if we need any virtual circuits, we can call it. This guy can create them, and it communicates. This one communicates only with the next machine. So is this one. The physical layer only talks to the next machine. Network layer talk to the next machine, but to actually understand the next machine, and to understand the entire network. Transport layer, that's level 4, never talks to intermediate machines. It doesn't know anything about them. It doesn't know how many machines, intermediate machines between here and Australia. The network layer will know exactly how many and which one are the best to follow. But transport layer can only talk with the transport layer at the very end there. So what does the transport layer need to know? Why, what functions could it do? One of them is called error detection. So this is what we call end-to-end error detection. You can do error detection between every 2 machines, but also transport layer can do it with the last machine. Channel 4 also, or transport layer, or layer 4, also does something called multiplexing and demultiplexing. What's multiplexing and demultiplexing? For example, if we have 4 users here, or 4 files, you want to send them over there to the same user. You can do it in multiple ways. You can ask, at this level, you can say, give me 1 virtual channel, and channel 4 and layer 4 here will tell layer 4 here, listen, virtual channels are expensive. This network is charging us per virtual channel. So instead of getting 4 virtual channels, I'm going to get 1. Get 1 virtual channel and put these 4 files through it. File 1, 2, 3, and 4, and send them at different chunks. But the data is carrying different segments from different files. But between this transport layer and that transport layer, they'll be able to separate them back into those original files. This is called multiplexing, collecting 4 sources into 1 single channel and separate them at the other end, and it's called demultiplexing. It could be the other way around. Maybe we have 1 user and has very big file and say, send this file. Transport layer might say, right, if I send this on 1 virtual channel, it's going to take a long time. So it might ask the network layer, if the network does not charge us for virtual circuit, might say, give me 5 or 10 virtual circuits, virtual channels, and takes this file, split it into different parts. So it's 1 file, but splits parts of it there, another part there, another part there, another part there. So that's demultiplexing. You take 1 file, you split it into multiple channels, send it, and as long as the transport layer at the other end knows about it, and they collect it. And how does it know about it? There's a bit of a header here. There's a header that tells that one, I'm splitting this file into 5 units, collect them, and this guy starts collecting them. So information is exchanged between this transport layer and that transport layer in those headers that they keep adding on top of the user data. So this is some of the functionality of the transport layer. Error detection, multiplexing, and demultiplexing. And usually, data link layer, what address does it use? What address is used at the data link layer level? It's called the MAC address. At the network level, the IP address. Thank you. And at the transport layer, it's the port number address. And just quick question. What is the MAC? What's the MAC address? Yeah?
A unique address that identifies a machine on the network?
On the wide area network, right?
No, not on a wide area network, on an internal.
On a local area network. On a small network, on our local network, every machine has a unique number called the MAC address. So it helps us. If one of our machines wants to send a message to one other machine, then it knows. We put that on top of the message so we know which one it is. All right, what about the IP address? Who would define the IP address for me? Is it a unique number in the same local network? What do you think? IP address.
In the same local network?
Pardon?
It's unique in the same local network.
On the same local area network. So it's the scope of IP address is a local area network. Don't think so. What is it? Where's the scope of the IP address?
For your networking, the internetwork number, each
Okay, so it's worldwide. So the MAC address is a unique number to identify a machine on a single local area network. The IP address is a unique number that identifies one machine worldwide. So if you want to send a file to a printer in China, you can send it if you have the IP address of that printer, and if you have access, of course. But if there was no restriction, you can actually send a file from here to China to a particular printer if you had the IP address. The IP address identifies one particular device worldwide, and it has to be unique worldwide. The MAC address, even though every MAC address is unique, but only we need it to be unique within a local area network. Now my next question, yeah? Do you have a question?
I was just going to say, your IP then would identify your local area network in the internet then, would it?
Yeah, but it goes as far as after most of the time you don't send a message to a network, you send it to a user, one of the machines on that network. So yeah, but the IP address will first look for the network. It's like with the postal system. If you send a letter to somebody in Australia with the name, you have his name and his or her street address. You never look at the name or the address. You only look at Australia until you get to Australia, where, what city, and then Sydney, and then. So same with the IP addresses. You look for where's the network, and then when you get to the network, then where's that machine? But it's the IP address consists of both, just like your mail address consists of maybe 2 or 3 lines. The next one is, what's the port number address? Port number? Yeah?
It identifies an application.
It uniquely identifies an application worldwide, right? Or on the local area network.
Yeah, there's like a table where there is port for every.
Let's say I have an application running on my machine, and this guy has an application on his machine, and you have another different application on your machine. Does the port number identify those 3 different applications on those 3 different machines? It uniquely identifies a program or an application where? Did you have a question or an answer?
No, I was going to say, like it uniquely identifies a channel of communication.
Yeah, okay, but then I guess they all, okay. No, the port number address uniquely identifies one application on one single machine. So on your machine, if you have 5 programs running, one is uploading a file to somebody in New York, and another one downloading something from, a video, and another one messaging somebody. So there are 5 of these programs running. When a message comes in, which program will it go to? That's defined by the port number. Any application that you run that needs to communicate outside your machine must first ask the transport layer, says, give me a port number. It's given a number. Now, every message that carries that number, we know it's coming to this program, not another program, that particular application on your machine. So if you run 2 or 3 applications, they'll have separate port numbers. You can probably have, I don't know, maybe 4,000 port numbers theoretically on your machine. Okay, so these are some of the functions that are done at different layers or different levels. The next one is called the session layer. Number 5 is session layer. This is no longer, this layer is no longer on modern networks. It's removed. And the next one is the presentation layer. Number 6. Presentation layer is, imagine if this was a company, for example, and the user is at the top is like the president of this company. And there's another company in China, for example, and one here in Ireland. Some of the rules apply. The president can only talk to the president. An engineer in our engineering department can talk to the engineering department. The president here cannot talk to an engineer in our department or someone else. So you must keep the same level. Also, now this guy wants to have some deal or some business with that guy, right, with the other company. So they write them a proposal. They might write it in English. But that guy doesn't understand English. So that's where the presentation layer comes in. You might translate it. You might translate it here to Chinese, or you might wait until you get there, and the presentation layer might translate it from English to Chinese. So that's where the translation should happen. That's called the presentation layer. But in computers, when computers started first, and there's still many computers, they have different presentation. Like you get a number 69. You display, or 65, you want to display it on the screen as a character. What does it come out of? As A, character A in the ASCII code. But if I send the same code that represents A on my machine, like remember, every time you press a keyboard, a character on the keyboard, it doesn't, the computer, you don't store B or C or A or X. You store a number. Everything goes in numbers. Number A is in the ASCII code is 65, B is 66, and so on. Am I right with the code? ASCII code, anybody knows the ASCII code?
That's the capital A, and then the lowercase is 90.
Very good. Okay, thank you. So I'm talking about capital A's. So let's say you press capital A, it's 65. Now I send it to your machine. If your machine uses ASCII code, it will display character A. If it uses different code, like EBCDIC code, might display a different message. So if I write a message in English and then it's sent in ASCII code, coded in ASCII code, goes to your machine, and if your machine is not ASCII code, then it will be displayed as completely different message. So in order to unify this, they had that layer. And now it's been removed. So a network really doesn't care what you want to transfer. You give us bits, we transfer them. If your machine, it's up to your machine at the very end. What the first network started saying, listen guys, we only deal with ASCII, for example, ASCII code. If your machine deals with any different, translate it before you give it to us. So, and if you receive it, change it to your whatever you code, but what you get from us is ASCII code. And now, it doesn't really matter what you get, you're just gonna get bits, and it's up to you how you translate them. So, it's no longer really available, the presentation code. The session is, again, in the old days, they used to log in to get onto a system. You must first log into the main device, the main frame, and that takes a lot of identification, multiple stages of identification and security checks. So any repeated sequence of actions, instead of getting the user to do them all the time, they can be implemented in the session layer. So one session of whatever sequence of events that are required at a given session, it can be done at that level. Sometimes encryption as well is implemented at this level. So these are the kind of 7 layers. Every one of them has a function. Everyone is there to provide a service to the one below it. There is communication called virtual communication that happens between peer processes. And peer processes are processes that are on the same level but on different systems, on different machines. As you can see here, this is network layer, level 3. The 2 below it, whenever they communicate, they can only communicate with the neighbor, no more. So they call this point-to-point or link-to-link communication. Anything over level 3, that's level 4 to 7, whenever they communicate, they have end-to-end communication. Level 3 is the only one that communicates with the neighbor, but really can communicate with the one after. They can really understand who is beyond the nearest neighbor. This is like the sorting office at the post office. These are the people that know the map of the world, and they know the flights and airports we have. Now, every level has a data unit to deal with. Physical layer deals with, what's the data unit here? It only understands bits. So this level only understands what a bit is. It doesn't know 2 bits together what they mean. They mean nothing. You just say, am I transmitting either a 0 or a 1? That's all. This guy here collects few bits together and looks at, what's at the data link layer we said? What's the data unit? Frame. Network layer? A packet. So if this guy wants to send a message, our user, it's a big message, it's broken into packets. This guy takes a frame and puts a packet into it and sends a frame. So a frame takes a packet in, goes from one neighbor to one machine to the next. The frame is removed, take the packet, pass the packet to level 3, level 6, say, no, send it to the next machine. Bring it down here, make a new frame, put the packet into it, send it, remove it off the frame, pass the packet. So packet moves here, PKT, and every time we want to move the packet to the next machine, we give it to data link that puts it into a frame. A frame is like a boat that takes this box from this location to that location. And we need a different frame each time from one machine to the next. What's the data unit used at the transport layer? It's probably a segment. Yeah. But there are general names for those. They call this the physical layer data unit. That's the bit. This is the data link layer data unit. This is the network layer data unit. So if you don't know the name, just use this general naming that was used by the original model. They just call the name of the layer and they call it data unit. So this one here would be considered transport layer data unit, TLDU. So if I ask you what's the unit here, tell me it's TLDU or segment. They're both correct. Segments are the newer names that are used on the network. So, and so on. And same here, session layer data unit, and presentation layer data unit, and application layer data unit. And the application layers contains any program that can allow the use of the network. Now, what's between one layer and the next? There's something called interface. So the interface is found between every 2 layers. And what does the interface does? Interface. So the interface is found between every 2 layers. Anybody knows what an interface is? If you run a program, first thing you see on the screen is the interface. Yeah?
It's if two, I say, different things want to communicate with each other. It's
Yeah.
practically the translator for between those two.
Okay. Let me tell you what the interface according to this model is. It's similar to the interface that if you run a program, you see a screen. For example, you run a program, a database program. It says, this, if you press this button, it will allow you to open a file. If you press this button, you'll delete a file. If you press, so it shows you what functions can be done. But the interface itself doesn't do anything. It does not implement any of the functions. It just tells you what services are available. So that's what an interface according to this model. And here, between every 2 layers, there's an interface that shows the higher layer what services the lower layer can provide. And also, the interface has what's known as service access point. That means it tells the higher layer when it asks for a service from the lower layer and the service is provided. Let's say transport layer asks the network layer, say, give me a virtual circuit, create a virtual circuit for me. And this guy does and creates it and comes back with the number. It tells the higher layer, where does it find that number? It's probably in memory location somewhere, or in a queue, or somewhere. That's called the service access point. Where do you actually access this service? And if you get a result, where do you actually find that result? That's called access point. But remember, every layer kind of encapsulates the data that comes from the layer above it. So this guy has a message, gives it, say, to the application layer, to this application layer. Probably this one says this is some kind of a message and it's coded in the header. So in the header here, this information written in this header only understood by the application layer there. For example, this application layer might say, take those 2 messages and join them together. In some signal to that one only understands it if he looks at the header there, so it joins them and removes the headers. This guy here might get a big message and breaks it into 2 segments. I might tell the transport layer at the other end, I have it broken into 2 segments, but I'm sending them on the same channel. So it'll know it through the headers. So this guy communicates with this guy, the program or the application here, or is communicating with this application here, exchanging information through the headers. This in there is user information, we cannot change it. It's like the error detection. When we did error detection, we take a packet, we say we can't change this, but we're going to do error detection. So we run this and we put the CRC at the end. So there's information added at the end. Who looks at this information? Who does it make sense to? Only this data link layer at this machine knows what this information means. This guy, network layer, doesn't know what that means, or the physical layer doesn't know. So at every level, only those 2 or entities that communicate together, they can exchange information through the headers. Through extra information, we call it headers. The network layer, this guy here says, I want to go to that machine in Australia. How does it know? Because it puts the IP address here. This guy never knows, doesn't know what an IP address is, never looks at it inside of it. So information is contained in extra headers. And all this, as this guy gets it, they say it's encapsulated. It gets it like a capsule. It doesn't know what's inside it. It doesn't read the information inside. It doesn't care what the information is inside it is. So it takes it. This guy, data link layer, doesn't know that the first 2 bytes are IP address and the next one are source address. It doesn't care. It's just going to send it, puts it in a frame with its own header and its own footer or trailer. This is called encapsulation, according to this model. So you need to know what encapsulation is. You need to know how does this entity convey information to this entity, or as to what it needs to do. Like error detection, what does it mean? They need to follow. So in order for this guy to tell this guy, I'm following CRC, or I'm doing parity check, they need to use one of those protocol. So this communication between these 2 is controlled by a protocol. This communication between these 2 is called by a protocol. Every entity, every virtual communication is controlled by a protocol. So if you ask somebody in the street, you ask them what a protocol is, what would their answer be normally? A set of rules and regulations, that's fine. But in this model, what is a protocol? It's a set of rules that controls virtual communication. And you say, what's virtual communication? Then you can deal. Virtual communication is communication that happens between 2 entities in the same layer. Remember, don't say communication between 2 layers. Layers don't communicate. Like if you have 2 buildings, in Italy, they have high buildings with balconies in very small roads. And you look at them and you can see somebody standing here talking to somebody here, and these 2 chatting. So it's the people chat, the entities, not the balconies. You don't say level 2 is communicating with level 2. No, it's the entity in level 2. So always communication happens not between layers, it's between entities or applications in different layers, on the same layer but on different machines. And they use virtual communication, which is controlled by protocols. And it has to follow a real route of communication that goes downward. Right. So that's the ISO OSI model. What does ISO OSI stand for? Anybody knows what the ISO stands for first?
International Standards Organization.
Thank you. And what's the OSI? What does OSI stand for? Anybody remembers?
I love my acronyms.
Hold on.
Organization, standard interface.
The International Standard Organization, ISO. OSI is
Open System Interconnection.
the Open System Interconnection. Right. Right. How many layers is in the OSI? 7. Right. Name them. Start. Name the first one.
Data layer, or it's like physical layer.
Oh, well, okay. The physical layer, number 1. Thank you. What's number 2? Layer number 2. Number 3. Network layer. Now, no. At the network layer, what's the data units used? Do they use, I'll give you a hint, do they use frames? Oh. No, not addresses, the data unit. A what? A packet, right. I was going to give you some hint. Right, at the transport layer, what data unit is used? Is it a packet or a frame or a bit? Yeah, transport layer.
PLDU.
Oh, okay. Transport protocol data unit. Or did I call it TL? It's not TP. It's transport protocol data unit, session protocol data unit, sorry. Not session layer. Okay. I gave you wrong information, right? So fix that. It's okay. What's the difference between layers above level 3? This is level 3. What's common between all these layers above it and all these layers below it? What's the difference between them? Anything you can...
1 to 3 is point to point.
Yeah, 1 and 2 are point-to-point or link-to-link communication, and 4, 5, 6, and 7?
They are end-to-end.
End-to-end communication. Yeah, perfect. Okay. No, no, that doesn't matter. Okay. What does the interface do? What function does the interface perform? Okay, and what's service access point? What do we mean by service access points? Service access point? Like here's a socket here. That's, I don't know, maybe if it's a power, then that's the service access point for electricity, or maybe the internet, then that's a service access point. But there are certain points where you can get the service, or that's maybe in different layers. Okay, that's where you actually get, where any service that's provided by a lower layer to the higher layer, where's the result of that service going to be available? Where do you actually get that information? The example I gave, transport layer says to, asks the network layer, get me a virtual circuit. So it's going to create it and come back with a number. Where does it actually find that number? That's the access point. What else do we do? What functions does transport layer, or is transport layer associated with, according to this model? Does it do routing? Does it do error detection? Yeah? Multiplexing and demultiplexing. What about error detection? Does it do error detection?
End-to-end detection.
Pardon?
End-to-end.
End-to-end. I thought I heard somebody saying yes. It's end-to-end error detection, not just error detection. Right. And what is virtual communication? What do we mean by virtual communication? Yeah?
When you
No.
appear
Yeah.
to be communicating with somebody like directly, but you're not.
Okay. Like I'm talking with the layer below me. I say, listen, I want to talk to you soon.
It goes down, the only,
So that's virtual communication going to the next level.
well, going down to the levels, across, and then back up.
That's real communication. That's not virtual communication. Real communication, the one that goes through the system, the wires, the transmitters down, and then the sound appears at the end, or the picture appears. That's called real root, real communication. What about virtual communication? How would you define it?
It is when a layer from one system connects with communicates with the same layer of another system.
So when layer number 3 or 4 talks to layer number 4, that's virtual communication. Is that?
Well, but it seems like we are directly communicating, but that's we're communicating.
So it's the layers appear to be communicating. Okay, so that's the communication that happens between similar layers. Is that what you're saying?
Yeah.
Anybody has any objection to this?
Not similar layers, the same layer.
Layer number 4, communicating together. That's what I think she means. Is that correct? Or layer 5 and layer 5?
I got it wrong.
Okay, just the point, be more specific. Layers do not communicate. It's processes on those layers or entities on those layers. So it's the communication that appears to be happening between entities or processes on similar layers but on different machines. But to make it even easier, say it's the communication that appears to be happening between peer processes. And then if you're asked what's peer processes, they are processes that are on the same layers but on different machines. Right, and what's a protocol? Anybody wants to volunteer a protocol? Set of rules, oh my God. A protocol, anybody there? Yeah? What's a protocol, gentlemen and ladies? Yeah? It's a protocol that controls virtual communication, right? Okay, yeah. So, I'm going to give you a function. You give me the layer where you think that function is. Virtual circuits. What layer performs virtual circuits? Network layer, transport layer, application layer, physical layer? Come on. Network layer. What about error detection? What layer performs? Yeah? Transport. No. What layer? Pardon? I was going to ask someone. Okay, it's not a wrong answer, but it's not a complete answer. In fact, error detection can be carried out at almost every layer. Layer 2, layer 3, layer 4. It depends on many different networks. Some networks do end-to-end. Some networks do at level 2. They do point-to-point. Sometimes some networks do it at the network level. Some networks do it at both. You know, level 2, level 3 sometimes. So it can happen at multiple levels, error detection. What about multiplexing and demultiplexing? Where do you think it happens? What layer? Layer 3, network layer, or data link layer? Layer 4, transport layer. What about encryption? What layer do you think it happens at? And they also changed this from the model. Encryption used to be a certain model here, but nowadays they say you do your own encryption. Networks don't encrypt. Pardon?
Presentation layer?
No. Session layer. Maybe, yeah. So it was kind of closely associated with the presentation layer as well. But now, sending an email. Sending an email. What layer? Layer 1, 2, 3, or 4, or 5, or 6, or 7. Application layer, or physical layer, or data link layer. Downloading file, FTP, file transfer protocol. If you have an application that does file transfer protocol, what layer would that be? 7, layer 7, the application layer. Any program that does a job, a communication job, or uses the network for something, there's an application up there. So if we talk about the application, it's the layer 7 at the very top. That's the users deal with that. So the user at the very top deals with the transport layer, says, I want to run email, so it runs email application, or I want to talk to somebody over the IP, voice over IP, VoIP. So that's an application. These are specific, more details. Now, which one sends 1 bit at a time? Transport layer. Which one uses headers attached to the messages? Which layer attaches headers to messages? Data link, wrong answer.
Multiple layers.
Yeah, give me examples. Like the physical layer, for example, right? Physical layer doesn't know headers, doesn't know nothing.
Yeah, it just...
Give me a layer that uses headers.
the network layer?
Network layer adds a header to the packets. What about data link layer? It adds headers to the frame, creates a frame, puts a header on it. So transport layer sends a segment and adds a segment, a header to the segment. Almost every layer adds an extra bit of information. We call it header. Why? Who looks at this header? Why? Why does some application somewhere along one of the layers adds header information?
The corresponding layer on the receiving machine will
The corresponding
read.
process on the same layer at the other end, they make sense of this information only at the same level that they can look at that header and they know what it is. The layer above it or below it, they don't know. They look at it as just encapsulation. There's just a capsule inside it. There's lots of rubbish, but you bring it to the correct level, and that rubbish makes sense. Maybe at the data link layer, say, oh, that's CRC information. That's the sequence number. Remember sequence number. This is an acknowledgement. They know what's in there. But the layer above it or below it, they don't know anything about this information in that frame header. So information in any header only makes sense to the same application on the same level. Which one is better? Layer 4 or layer 3? Okay. And don't say it depends. It doesn't depend. Every layer has its own job. Right, tell me something else. Okay, guys, thank you very much. The tutorial is going to be on Moodle on the page. It's already on Moodle, but it's invisible to you, so I'll make it visible and have fun with it. See you. Thank you.